everyone. I'm Leonard Apelson. I'm the author of Data Science Bootcamp, 5 Python projects, and today I'm going to be talking with you guys about how to uncover friend groups in social networks. So, what do we mean by a social network? A social network is a graph uh, where the nodes represent individual people and the edges represent connections between these people. So it could represent connections between coworkers, between friends in social media, between friends in real life. And we're going to explore this topic of social networks in more detail by starting out with a very concrete example of one of the most well studied social networks out there called Zachary's Karate Club. So, who is Zachary? Well, Zachary was a sociology student in the 1970s who happened to have joined a karate dojo. And over the course of a year, he recorded friendships between people in the dojo. He would monitor, which members of the dojo would go to get a beer or hang out after class. And if they hung out frequently, he put a friendship edge between those two individual people. And if they didn't, then there was no edge. And in this way, he had built up a social graph. Now, a year into this analysis, something interesting happened. One of the instructors at the dojo, Mr. High, got into an argument with management and decided to go off and start a dojo of his own. And about half of the karate class leaves and goes off with Mr. High. And when Zachary took a look at the structure of the network that he had built up over the course of the year, he realized that he could predict with near perfect precision which members of the class joined Mr. High's new dojo and which members of the class stayed behind. So, how did Zachary do this? Well, we can take a look by loading in the actual Karate Club network from Network X, which, of course, is the popular external Python network and graph analysis library. So we're going to load the Karate Club graph stored in the graph Karate, and we're going to print out all the node attributes within the graph, where nodes, of course, refer to individual students. And here, the node attributes refer to whether or not each student went off to join Mr. High's new dojo or stayed behind. So the Mr. Cly attribute refers to whether the student signed on with Mr. High. So we have this network containing 34 nodes. And what we're going to do now is we're going to visualize the network using what is called a force-directed layout, and I'll explain what that is shortly. But we're going to visualize this network in 2D space, and we are going to color the nodes in the network. And so those nodes, those individuals that joined Mr. High's new dojo are going to be colored black, and those who stayed behind are going to be colored blue. So let's visualize the network. Okay. Here we have the visualized network. We visualized it using a force-directed layout. Now, force-directed layout visualizes a network using basic concepts from physics. So each node, each person is treated like a negatively charged electron, and negative electrons repel each other. So the nodes try to get away from each other as far as possible. But the edges are treated like springs, which tend to bounce back and try to draw the nodes back in, so the nodes cannot get too far away. And when you model the forces in this physical system, the nodes that are tightly interconnected by springs all bounce or draw in and clump together, and so eventually the physics stabilizes into kind of a coherent network at equilibrium. So when we do this visualization, we notice a number of things. First of all, these nodes, these people network, form kind of two discrete clumps in 2D space. We see kind of two groups of people, and each group has nodes that clump together. And as a reminder, the nodes are colored by whether or not the student went off to join Mr. High or not. So the Mr. High nodes are all here in black. And we realize that one of the two clumps is all black, representing a tight, a tight connection of friends that all went off to join Mr. Kai's dojo. And when we think of this network in these terms, then kind of we understand what's going on and how Zachary could predict who would join up with Mr. High. It seems that within networks, in a visualized network, tight clumps of friends represents tight social circles of people that like to all hang out with each other. And the people that went off to Mr. High's dojo were just doing what their friends were doing, and they didn't want to break up that social circle. So this type of pattern repeats itself all the time in social graphs, and we can prove this by visualizing a much more complex and realistic network. We are about to visualize social network representing real Facebook data. This is data that's publicly available. The individual people have been anonymized, uh, so we don't know their identities. All we know is that they're friends on Facebook. And this network is going to be very large. It's going to take thousands of nodes. So we're going to load it in and we're going to visualize it. And it will take some time to visualize. We're waiting for it to visualize right now. It'll take about 30 seconds to a minute. So this is a very large social graph. It has 4,000 nodes, so 4,000 people, and nearly 90,000 edges, so nearly 90,000 digital friendships on Facebook. The reason that this is taking a long time to visualize is because force-directed layouts run in an order of n cubed, where n is the sum of nodes and edges. So this is on the order of nearly 100,000 cubed. And that's something I want to impart. Graph visualization takes a long time to run, and hence we can't use graph visualization to begin to uncover these types of friendship groups, even though they're clearly visible in the graph once the graph has finished visualizing. So we're waiting for this to finish running, and here it is. We visualize the Facebook graph, and as before, we see these tight clumps. These tight clumps represent social circles of people that are all friends with each other on Facebook and presumably all hang out in real life. And there's some really serious value for, let's say, an organization like Facebook to be able to obtain this type of data. For instance, you can imagine a Facebook employee might, program an algorithm where somebody who just joins Facebook is only friends with a few people, but using the social circle structure of the graph, Facebook can come up with new recommendations for that person. The value here is, and the applications are endless. And again, what I want to point out is that in this network, I just want to emphasize, we see tight clumps when the network is visualized in two-dimensional space. So these types of clumpy networks are called community networks. The clumps themselves, these clusters, are called communities. And the process of discovering communities in an automated way is called community detection or graph clustering. And there are a multitude of algorithms out there to carry out graph clustering. Some are better than others. For instance, we could theoretically implement an algorithm that embeds this network in 2D space using a force-directed layout and tries to find the clumps, the communities based on the 2D distribution. But of course, this is grossly inefficient. And so we're going to implement a different algorithm. And today, I want to explore one particular type of graph clustering algorithm called Markov clustering, or MCL. And Markov clustering is a fascinating algorithm, not only because it's elegant and easy to implement in a few lines of code, but because it also touches many other fundamental network analysis algorithms, some of which we're used to empower billion-dollar businesses. So we're gonna learn a lot here. And Markov clustering looks for community patterns in network data by analyzing traffic between nodes, traffic between friends. So what does it mean to have traffic between friends? Well, we can imagine traffic as being the flow of, text messages between friends or interactions in real life, but it's still a bit of an abstract concept when applied to the friendship space. So to make this analogy more clear, we're still going to do community detection using traffic, but instead of looking at communities of friends, we're going to look at communities of towns, uh, interconnected by roads, where towns in the same community or in the same county have more roads connecting each other. And we're going to look at model the actual traffic patterns between those towns to figure out how to uncover those communities. And then we'll eventually apply our learnings to the social graph. So what we're going to do is we're going to start by modeling a network of counties and towns. And to start, we are going to simulate, we're going to start by simulating a single county, and that county is going to be made up of 5 towns. So we're going to start by creating the 5 nodes in the county, all of which have this county ID attribute assigned to 0 because they're all in the same county. And now that we've created this county of 5 towns, we are going to model roads between towns. These roads are going to serve as edges. And we're going to assume that if towns are in the same county, then it's very, very likely that there's a road between them. We're going to assume that 2 towns in the same county have a 90% chance of having a road between them. So let's randomly simulate roads between pairs of towns in the county, and after our simulation is complete, we'll visualize the result. Yeah. So here we have a single county with 5 towns tightly interconnected by roads. We see there's a road from every county to every other county. And now so we've created a county 0. Now we're gonna model a second county, county 1. And we're going to assume that the county has between 3 and 10 towns. It's a value that we randomly select. And again, there's a 90% chance of there being roads between any 2 pairs of towns in the county. So here, we created county 1. It has more roads than more towns than county 0. And we see that most, but not all the towns are directly interconnected by roads. For instance, there's no road between town 5 and town 4. Now we're going to merge these 2 towns into a single graph using NetworkX's disjoint union function and visualize the results. So we have 2 distinct counties, but there's no roads connecting these 2 counties. And we're going to assume that there should be at least some roads connecting the counties. And now we're gonna simulate these roads again using, as before, random simulation. But we're gonna assume that the probability of any 2 towns in 2 different counties having a road between them is quite low. In fact, we're gonna make that probability 5% and see what happens in our random simulation. Okay, now again, the 2 counties are connected by 2 roads via random simulation. As you can see, this county has a community structure when visualize this county graph, aka much like with the karate network, we see 2 separate clumps. And we can kind of tell already what the 2 counties are without even knowing their identities in advance. But let's make things more interesting. We're going to raise the number of counties that are interconnected from 2 to 6. So let's simulate 6 interconnected counties. And here we get a much more nuanced graph, but that's also clumpy as expected, where the clumps represent communities. And let's actually color these clumps, these communities, by their county ID, and we expect again all the clumps to correspond to counties, which of course they do. And we can see here that they're, as expected, the towns in individual counties are tightly interconnected and by roads, and the towns in different counties have more sparse roads between them. So now what we're going to do is we're going to operate on the assumption that, if that counties, the towns in the same county have generally more traffic between them than towns in different counties. And we'll discuss that idea in more detail shortly. But first we need to define what exactly we mean by traffic between counties. And more importantly, how can we simulate and model that traffic mathematically? So let's start very simple. We're going to try and model, rather than modeling traffic, which is composed of multiple cars, we're going to model travel of a single car using random simulations. This is what we're going to do. We're going to pick a random town, let's say town 0, and we're going to assume that a car starts in that town. And then the car is going to travel to one town over purely at random. So the car is going to pick one of the X edges at one of the X roads leading out of town and go to a neighboring town. So let's say we start in town 0 and go to town 3. And now in town 3, the car wants to travel yet again, so it's going to pick another random road leading out of town and maybe go to town 6. And then it does that yet again and maybe go back to town 3. And then maybe it goes to town 7. And this way, the car is randomly bouncing around from town to town. And we can simulate this, and we can make a concrete simulation. It says, like, given a car that starts in a random town, let's simulate its journey across 10 different towns and see where the car winds up. So we do that here. Again, we start off by picking a random town where the car begins, and then at each iteration, we pick a different road out of the town, and then select the town linked by that road. So let's do this. We're going to have a car drive around randomly, and it has reached town 24. Well, big whoop. But now that we can simulate the path of a single car, we're going to simulate traffic. And we're going to assume that traffic involves, tens of thousands of cars all driving around from town to town. So we're going to simulate traffic using 20,000 cars. We're going to keep our model very, very simple. We're not going to assume that there's a limit to the number of cars that can be in any individual town or in any individual row, which is unrealistic but very useful for our purposes. And all we really care about is that there's 20,000 cars. Each car starts at a random town, makes 10 different stops, and winds up at some other town. And what we want to know is, at the end of the simulation, what is the most heavily trafficked town with the most cars, and how many cars are in that town. So let's run this random simulation across 20,000 cars. So this is running. Here we go. We learn after our simulation, we found that town 12 has the most cars. It has over 1,000 cars that randomly wind up in the town. And if we review our original network, we see that town 12 is very centrally positioned. There's a lot of in our visualization, a lot of roads linking in and out of town 12. And it's not surprised that it shouldn't be surprised that it's so heavily trafficked. As opposed to, let's say, town 3, which is off to like in a single county on the side. It doesn't link to so many counties. So there's still a lot of roads leading in and out of town 3, but in our visualization, it's not so central. So maybe, we would intuitively expect the traffic in town 3 to be slightly lower. And let's see if that's the case. So we're going to print the number of cars that are in town 3. And there are a little over 900 cars in town 3, which is a lot, but less than 1,000 cars in town 12. And at this point, I want to say that looking at these numbers, like 900, 1,000, these are hard numbers to compare to. I mean, they're easy to compare, but they're large. And in data science, sometimes it's more intuitive to take large numbers and to normalize them, where in our case, we would normalize by dividing by the total number of cars, 20,000. And this would transform our values from like large numbers to probabilities between 0 and 1. So this would give us the probability of winding up in town 12 at random after making 10 random stops, or winding up in town 3 at random after making 10 random stops. And let's just normalize our values now and look at the probabilities. So there's, as we can see that there's about a 5% chance of winding up in town 12 after 10 random stops, and about a 4.7% chance of winding up in town 3. So we're more likely to wind up at town 12 than town 3 at random. Because town 12 is more centrally positioned, we're not concerned with that right now. This is where it gets cool. So we computed these probabilities using random simulations, which is really inefficient. but we can also compute these probabilities directly without any sort of simulation using very, very simple matrix algebra. So we can compute these probabilities directly using matrix multiplication. And right now I want to talk a bit about how and why that is the case. So the reason that we can use matrix multiplication is because in math and data science, every network can be represented as a matrix called an adjacency matrix, and I'll explain what that means shortly. But I'm going to convert this network X class structure G into an adjacency matrix using network X's to NumPy array function. And I'm going to print out this adjacency matrix. This is what we get, a 2D table of zeros and ones. Each row and column in the table represents a town. So we have 31 rows and 31 columns corresponding to our 31 towns. And so for instance, the first row here, row 0, represents town 0. And each column J in this row determines whether there's a road linking between town 0 and town J. So if there is a road present, that the road is demarcated by a binary 1. Otherwise, it's demarcated by a 0. So looking at, for instance, row 0, we see that there's no roads between town 0 and town 1. And there's no roads between town 0 and town 2. There's a road going to town 3, and a road going to town 4, and a road going to town 6, and town 7, and one more town. And also I want to emphasize that we're looking at town 0 row-wise, but we could also look at this column-wise and get the same types of patterns because this matrix is symmetric, since inbound edges, inbound roads, there's no direction to the roads. There's no one-way road. So this matrix is symmetric. So what's cool about this is that we can begin to do some math on these rows. For instance, we can, if we sum up all of the values in row 0, we're going to basically sum up 5 ones and a bunch of zeros, and we're going to get a sum of 5. 5 represents the number of roads leading in and out of town 0. And if we divide that value 1 divided by 5, we're going to get 0.2, which is the probability of driving from town 0 to any other neighboring town. And again, we can compute this probability directly by summing either, let's say, the probability directly of leaving town 0 for any neighboring town, by summing either the row or the column, it doesn't matter, and taking the inverse of that, aka dividing 1 by the sum. So if we compute this value, we get, as expected, 0.5. The probability of traveling from town 0 to one of its 5 neighboring towns is 0.2. Boring, and as expected, but we did it using simple math. So let's take it up a notch. What we can do is we can compute this we can take this probability, and then we can multiply it by all of, let's say, all of the values in row 0 or in column 0. And what that is going to give us is what's called a transition vector. And the transition vector is basically the probability of going from a particular town to any town J. So looking at this transition vector, we see that the transition vector represents town 0. And we see that element 1 of that vector is 0, which means that the probability of traveling from town 0 to town 1 directly is 0, because there's no roads between them, not surprising. Whereas the probability of traveling from town 0 to town 3 is 0.2, because a road exists between them. And so this is a more kind of a coherent way of tracking all of these transition probabilities. Again, we can another simple way of computing it is by taking a adjacency matrix row or column, it doesn't matter, and dividing it by the column sum. So we computed the transition vector for a single town, but we have 30 other towns in our graph system. So we would want to compute transition vectors for them as well. And we can store all of these 31 vectors in a single table, which is a matrix. And this matrix is known as a transition matrix or also a Markov matrix. It basically tracks the probability of transitioning from any town I using to some other town j. And in NumPy, computing a transition matrix is incredibly easy. We just take the matrix itself and divide it by the sum across all of the matrix columns. And here we go. We have a transition matrix. It looks exactly like the adjacency matrix we looked before, only now the values are no longer binary. They represent probabilities. And in fact, in this implementation of the matrix, each column represents the probability of transitioning from a town to its neighbors. So column 0 represents the probability of transitioning from town zero to the neighboring town. So we have this probability matrix keeping track of our transitions. That's all well and good, but why do we care? Well, this is where the magic happens. With a bit of math, we can use the transition or Markov matrix to compute the probability of reaching any town after n stops. All we really need is to assign a vector of starting probabilities v, which basically says v, each index of v corresponds to the probability of randomly starting in any town. Now, in our random simulations, we had assumed that a car can start at can start at any one of our 31 towns equally. So the transition, each element of our starting vector v will be equal to this uniform probability of 1 divided by 31. And so basically v, our starting vector, is just 31 elements, each one of which is equal to 1 over 31. Okay, this is where it gets fun. If suppose we want to know the likelihood distribution of reaching each of our 31 towns after 10 stops, all we need to do is take the starting vector v and take the product, matrix vector product between the transition matrix and vector v. In NumPy, taking a matrix vector product is very easy. We just use this @ operator. I'm not really going to get into the math right now. I wish I had the time, but I'm not going to. But if you want to learn more about matrix vector products, please check out my book, Data Science Bootcamp. So all we got to do is do this operation, v equals transition matrix and at v 10 times. And if we do that, that will return a single vector of probabilities corresponding to the likelihood of visiting each town j after 10 stops. So we are about to compute the direct probabilities for all our simulations in just like 2 lines of code. Again, I can't really get into the math right now why this works, but the math is very straightforward, and it's all in my book if you would like to learn more. So before we compute these values directly, let's just quickly take a look at our the probabilities returned by our simulations. So we saw that there was a 5% chance of winding up in town 12, 4.7% chance winding up in town 3. This was based purely on simulations. And now we are going to compute these values directly. We're going to compute this probability distribution and output the probabilities. And they are exactly identical. We don't need to run a simulation. We just need to take a matrix vector product over 10 iterations. So these 2 lines of code form the basis of what is known as the PageRank algorithm. It was invented by Larry Page, the co-founder of Google, and Larry Page used this algorithm to basically turn Google search from a grad school project into a billion-dollar company. So the reasons these probabilities are important is because more central locations in the network have a prior probability of being randomly reached just by bouncing around, And when you apply that logic to networks of web pages rather than towns, then you can build a search engine where higher likelihood web pages are, rank higher in your search query results. So we've basically just replicated what was $1 billion algorithm in a few lines of code, which is pretty cool. However, our goal here isn't to build a search engine. Our goal here is to cluster social graphs into friend groups. And more concretely, we want to find the 6 counties in our town network using traffic simulations. And now we're going to take the concept of the transition matrix, aka the Markov matrix, and tweak it slightly to come up with what is called Markov clustering, which again is a very elegant way of computing these community kind of community clumps in just a few lines of code. So again, keeping in mind what we learned about traffic, let's turn to community detection. As a reminder, this is what our network of towns encompassing counties looks like when we don't know the identity of the communities in advance. We can still see the clumps. We just don't necessarily know exactly where the counties are because the colors have been eliminated. And this is where the concept of traffic comes in. We're gonna make the sensible and intuitive assumption that if you let's say you start at a random town and you bounce around in your car a bit, you are more likely to wind up in a town that's in the same community than a town that's in a different community, which means that you're basically more likely to travel to a town in the same county, and the sense of travel between towns, traffic back and forth, relates to a concept that's called flow. So flow is an abstract concept that comes up in graph theory and in a variety of branches of graph theory, and there's different ways of defining it. But in our case, we are gonna define flow using a very, very simple definition. We're gonna say that the flow between town I and town J equals the probability that if I start my car in town I, I'm going to wind up in town J after two stops. So very, very simple definition. So this is very, very close to our initial definition of the transition matrix, where ij corresponded to the probability of traveling directly from town I to town J. But now the travel is indirect because it requires 2 stops. How do we compute this flow matrix? Well, it's actually very, very easy to compute. So the flow matrix is just the matrix product of the transition matrix and itself. It's very easy to show why using the associative property. So remember, if you have a starting vector v of probabilities, we can compute the probability distribution and winding up after, at any town after 2 stops by running transition matrix at v. So which basically means that if you remove this v, this transition matrix at transition matrix multiplication will give us the two stop transition probabilities directly. So again, that's the math. It's discussed in more detail in my book, but that's basically the math. We can also prove out our assertion another way. I'm actually going to run a random simulation of cars just like randomly traveling, and I'm actually going to compute the flow matrix using the frequencies of my simulations. And then what I'm going to do is I'm going to assert that my simulated flow matrix is nearly identical to my theoretical flow matrix that I computed as this as this matrix to matrix product. And so the simulation takes a few seconds to run. But there, it's ran and the assertion didn't break. So yes, transition at transition matrix is equal to our definition of flow. So why do we need a concept of flow? Well, I am going to make the reasonable assertion that flow between two towns is larger if they are both in the same county than if they're in different counties. AKA, this corresponds to our notion that we're more likely to bounce around and travel from between two towns in the same county than we are between two towns in different county. And we're going to test this assertion using this bit of code, and it looks like a lot, but really all I'm doing is I'm computing two histograms. Uh, One histogram corresponding to the flow between all pairs of towns that are in the same county, and one histogram between all pair of towns that are in different counties. And then I'm gonna visualize this histogram using Matplotlib's hist method, and as well as outputting some statistics of the differences between histograms. So this is what the histograms look like. We have this blue histogram right here, which corresponds to their intra-county flows, the distribution of flows between towns that are in the same county. And you can see that this histogram is kind of much more out there to the right than this brown or beige histogram of inter-county flows between towns that are in different counties. In fact, there is about a threefold difference between the averages, between the means of the two histograms. So if two towns are in the same county, they're much more likely to have a larger flow. What's also interesting is this vertical line right here that I'm calling the intra-county threshold. This is the minimum flow this is the minimum observed flow between towns that are in the same county. And this threshold is approximately 0.042. And so given this threshold, we can isolate 132 pairwise examples of towns that are connected by edges and are in different counties. So theoretically speaking, if we have this threshold, we can just filter out all the edges below the threshold, and ideally we would eliminate many of the edges between towns in different counties. That's just if we have the threshold. Now here's the problem. The only way to obtain this threshold is to know the identity of the counties in advance. And we don't know the identity of advance. So let's say if we were looking at this graph blindly, we might pick a threshold of our own. We would pick a low value, let's say like 0.01. And that value would be inappropriate because right now the actual threshold is 0.042. So suppose we were to assign our own value based on our intuition, we would keep a threshold value low, and we would ask ourselves how many edges in this data, how many of the inter-county flows fall below a threshold of 0.01, and it would be 0. This threshold is it's not that this threshold we guessed is worthless because the difference between intra and inter-counties flows is great, but it's not that great. It's not big enough. This vertical bar needs to be more, it needs to be smaller, it needs to be more to the left. And what we really want to do is we want to exaggerate the differences between flows. You want to make the difference between these two these means bigger. You want to push the blue histogram more to the right, the beige histogram more to the left, and more importantly, we want to make this threshold that can be used to isolate flows corresponding to towns in different counties. We want to make this threshold as small as possible. So how do we exaggerate the differences between histograms? Well, as a reminder, all of the values in our elements of our flow matrix are less than or equal to 1. And for any vector whose values are less than or equal to 1, we can exaggerate the differences between between elements in that vector using a very, very simple process called inflation. So in order to inflate a vector, all we really got to do is square all the elements of the vector and normalizing it by dividing it by the sum of the elements, aka converting it to probability. So let me show you a concrete example. We got a very simple vector whose elements are 0.7 and 0.3. And if you want to make element 0, 0.7, you want to make it larger, and we want to make 0.3 smaller, but at the same time, we want to make sure that 0.7 stays larger than the mean, which here is obviously 0.5, and we want to make sure that 0.3 remains lower than the mean. So we're going to do that in a two-line operation. We're going to square all the elements of V, and then we're going to normalize by the sum and output the final vector, as well as the corresponding means of the final and the original vector. So 0.7 has become much larger, well, noticeably larger. It went up to 0.4. 0.3 has become noticeably smaller. It went down to 0.15. So the variance of elements in this vector has been exaggerated, but the mean has remained the same at 0.5. So things that are smaller than average have gotten even smaller. Elements that are larger than average have gotten even larger. And so we've effectively inflated the vector. And we can apply the same concept of inflation to our entire flow matrix. And it's very easy to do in NumPy. Before, it's just 2 lines of code. We square all the elements of the matrix, and then we divide the matrix by its columns sum. And if we inflate the flow matrix, the difference between the two histograms should be much more extreme. So let's see if that's the case. So it worked. The gray, the beige histogram of flows between towns in different counties is now way more to the left. And now the the means of there's like now if you look at this mean output, there is now a 7-fold difference between the flows of towns in the same county and flows of towns in different counties. More importantly, this vertical threshold right here, corresponding to the minimum inter-county flow, is now much, much smaller. It went down to 0.012, and it can be used. There are 100. There are like 118 pairs of towns that can be used that this threshold identifies as not being in the same county. So the threshold, our approach worked. The threshold is smaller, but it's still not at 0.01. It's smaller, but it's still not small enough. And so if we had randomly guessed a threshold of 0.01, we would still not have obtained efficient or any valuable filtration of edges corresponding to towns in different communities. So how do we make this exaggerate the differences even farther? Well, we're going to do that using a very simple operation. And this is going to work. I'll explain why this works shortly, but first I'm just going to show you the operation. I'm going to take the product of flow matrix with itself, and then I'm going to inflate that result and recompute the distribution. So 1 line of code. I'm going to inflate flow matrix. I'm going to inflate the product of flow matrix and flow matrix. And let's see what happens. Let's prove that this works, and then we can talk about why this works. And doing the inflation, and there we go. The beige histogram has become so small, it's basically non-existent. You can't really see it in comparison to the threshold, but it's there. And the threshold that divides the inter and inter-county flows is now tiny. It's 0.001, and 541 pairs of towns that are in different counties have a flow below that threshold. So a combination of inflation and matrix multiplication has worked. And here's the real kicker. If we do this long enough, if we repeat this over 20 iterations, multiplying matrices and inflating over and over and over again, eventually the flow of all of the pairs of towns that are in different counties should fall to 0. So I just ran this command. What's going on here? Why is this working? Well, one way to think about it is to kind of like take a concrete analogy where let's say let's say you have a network of roads, and there and there's a Department of Public Works that's responsible for maintaining roads, but they have a limited budget. So they're only going to invest in maintaining those roads that are more heavily trafficked. And so less heavily trafficked roads aren't going to get maintained. And so maybe those roads, they get a little cracked and they're harder to drive down. And so it's going to make people less reluctant to take those roads, and traffic on those roads is going to drop even more, which means that the maintenance budget for those roads is going to get even smaller, and it's going to lead to a feedback cycle. And this is what we're modeling right here. So we're basically using taking the product of the two of flow matrix with itself to measure the traffic between roads, and then we use those measurements to figure out which roads get more maintenance and which roads get less maintenance. And we're going to do that through inflation. So via inflation, roads that get less traffic get less maintenance. But as consequence of that, roads that get less maintenance are going to be, going to get less traffic, hence less maintenance, hence less traffic, and hence less maintenance. And this is what's going to happen. We're going to start with a system of roads where roads within counties, per our intuition, are getting slightly more traffic than roads between different counties. And which means roads between different counties get slightly less maintenance, which means they begin to decay, which means their traffic goes down, which means they get even less maintenance. And eventually what happens is that the roads between counties crumble completely from disuse. And it's impossible to drive from any county to any other county because no roads exist, connecting them, which again is terrible from a public infrastructure perspective, but really great and useful for our particular algorithm that's intended to eliminate roads between communities while keeping the roads that are within communities. So let's check the output of our algorithm. Supposedly, this cycle of inflation and multiplication will have caused all of the flows between towns in different counties to have dropped to 0, which means the associated edges we suspect represent pairs of towns that appear in different counties. So let's actually count the number of suspected edges that we suspect of appearing between counties. So we have 57 such edges in our town graph G. So now what we're going to do is we're going to delete these edges from a copy of the graph. And what we expect to see is that we expect to see our 6 counties completely isolated from each other after the edge deletion. So let's see what happens. Well, so we got a result, and our results are pretty good, but they're not perfect. So right here, this county 0 perfectly isolated and perfectly preserved. So is this this bluish county right here. So is the violet county here. So is this pinkish county here. We've isolated them correctly. But then if we take a look at the 4 towns in the yellow county, towns 9, 10, 8, and 11, well, these towns were all in the same county, but we've inadvertently deleted some of the roads between them. So our algorithm has partially failed, and we want to explore why. And the failure is driven by the following. So our model of traffic is a little wonky in some respects because it does not allow. It always forces a car to travel from a town to some other town at each iteration. It does not allow a car to ever stay in place. And this makes sense if the car is maybe like a criminal that's on the run, but occasionally you just want to sleep the night. and like stay in the town that you're at, and then like do the touristy things and see the sights, and then move on. And our model of traffic does not account for that. So what are the consequences of that? Like imagine a simple scenario where you just have two towns, A and B, and there's one road between them. Well, in that scenario, a car that starts at town A is always going to be forced to travel in town B. So its first stop is always town B. And then from town B, it can never stay in town B. It's always forced to travel back to town A, which means the second stop is always town A. And so it's always bouncing back and forth between town A and town B, and its second stop or its even stop is always town A. And consequently, the flow between town A and itself is 1, but the flow between town A and town B is 0. There's 0 flow, which doesn't make sense because the car is constantly visiting town B. So how do we deal with this inconsistency? Well, we need to introduce a way for the car to optionally remain in town A rather than going in town B. And we can do that by imagining an edge, imagining a road that goes from town A to itself. So if you take that road, you're basically going to do a U-turn. You're going to take the road and you're going to drive a bit and you're going to wind up directly where you started from, town A. So essentially, this loop is equivalent to staying in place and not going anywhere at all. Again, this type of edge between a node and itself in graph theory is called kind of a self-loop or a buckle. And by introducing self-loops, we basically prevent this weird bouncing back and forth that is causing error analysis. And the best way to introduce loops, like we can take an adjacency matrix and just add ones across its diagonal, and we're going to introduce loops in that way. So here we're actually going to model the scenario we discussed. We're going to have an adjacency matrix M1, which represents town A and B, where you're always forced to go from A to B and vice versa. And we're going to have M2 with self loops on the diagonal, where you can optionally, from town A, you can go to town B, or you can take this self loop and stay in town A. And we're going to compute their flows. So just as expected, the flow from A to B in the first scenario is 0, and the flow from A to B in the second scenario is 0.5. In this sense, these self loops are the real missing piece that we need to implement Markov clustering, or MCL for short. And if we implement it, then we can get the clustering right. So here we are going to introduce, we're going to define a run MCL algorithm. It's going to take a G, and it's going to assign self loops to all the nodes, to all the towns in G. So it's basically you assign a loop to each node by basically adding an edge from node I to node I. And then we just repeat our existing implementation of the Markov of our algorithm. We get the adjacency matrix, we compute the transition matrix, we use that to compute the flow matrix, and then we iteratively inflate the product of the flow matrix and itself. And again, as a reminder, I'm going to emphasize that the real magic happens in this two-line iteration, which is very analogous to kind of the two-line iteration that we use to implement PageRank. The two algorithms are intrinsically similar to each other. And then once we've inflated and multiplied a flow matrix over enough iterations, the flow between counties and different towns and different communities should have dropped to 0. So we're going to delete all edges with 0 flow. So let's do that. We're going to run this MCL implementation, and then we're going to visualize the results. And here we've perfectly we've perfectly isolated all our 6 counties. So all the roads between different counties have been eliminated. And now let's say if you're in county 1 right here, there's no county 0 right here. There's no other way of traveling to any county. So you're stuck. These like isolated clumps in space are known in graph theory as connected components. Identifying connected components in a graph is very easy. You can use it. It's kind of like one of the most basic graph algorithms out there. You can use it using a basic breadth-first search. I'm not going to get into the details of the algorithm because unfortunately I don't have time. But if you'd like to learn more, please check out my book, Data Science Bootcamp, and we discuss the algorithm in much more detail. However, Network X has this very convenient connected components function that we're going to apply to our graph and get out all the connected components, which are basically our clusters. So we know exactly, we get back our 6 counties corresponding to our 6 clusters, and we know exactly the identity of all the towns in every cluster. So we've basically just implemented Markov clustering from scratch in a few lines of code. And now our implementation is going to work well for like small to medium sized graphs. There's additional optimizations that can be done to run MCL on a much larger scale, which I'm not going to get into here. But if you do want to run MCL on a larger scale, I suggest you use the external Markov clustering algorithm, which you can obtain by pip installing Markov clustering. Once you've obtained this external library, you just import get clusters and run MCL functions from the library. And given any adjacency matrix M, you can get back all the clusters just by running get clusters run MCL M. So I'm actually going to run this command on our adjacency matrix of towns and see what happens. Oops, let me import from the library, run the command. And here, we've perfectly reproduced all of our clustering. So with this in mind, let's turn back to our social networks. Okay. Our Markov clustering algorithm that works on communities of towns will work equally well on communities of people. For instance, let's revisit our karate club network from the start of our discussion. Here's a reminder, this is what the network looks like. 2 clumps, 2 clusters of black nodes correspond to those karate students that went off to join Mr. High's dojo. And now we're going to look for these clumps using the installed implementation of the Markov clustering algorithm. So we run get clusters run MCL on the adjacency matrix associated with G Karate, and we get back 2 clusters as expected. And now what we're going to do is we're going to re-visualize this network, but we're going to color it by cluster ID rather than known dojo label. And our visualized network is nearly identical to kind of like the real world dojo representation. There's one slight difference right here. I think here's an example of an individual that joined Mr. High's dojo that in our network is predicted as belonging to the other social group, but this one false positive corresponds to an individual that's right between the cusp of 2 social groups. So this individual is a bridge between 2 different social circles, and we can capture these bridge nodes, these people that bridge different social groups together using the results of our Markov clustering, our outputs. So with this in mind, I want to now let's turn to the more complex Facebook network. I'm not going to revisualize the entire network from scratch because it will take a while. The uncolored network from scratch. I don't want to. As we saw before, it took about a minute to visualize that network. But let me just run MCL clustering on the Facebook network. And it took about a second to run on our 4,000 people, 90,000 edge Facebook network, and we obtained 10 clusters. And now what we're going to do is we're going to take these 10 clusters and we're going to visualize them on the Facebook graph. So we're going to color each of our Facebook individuals by their associated social circle cluster. This will take a while. So this is, again, as we saw before, the visualization is the Facebook visualization takes a while because the network is so large. Let me just quickly scroll up to remind you what what the network looked like initially before before any sort of clustering and coloring. We see these tight community clumps in the network, which we believe to correspond to social circles. Uh, and our expectation is that each of the clumps within this Facebook network will be assigned its own unique color by the time by the time the visualization is complete. So let's wait and see uh, what happens. Again, apologies for the long wait time. As a reminder, uh, network visualization can be a very slow process, and that is why we can't cluster nodes that way. But now the visualization has completed, and here it is, the final network. It matches our expectations exactly. We the various clumps in the network that we believe correspond to social groups, and all network theory, according to network theory, these are definitely social groups of tightly interconnected friends on Facebook, have been correctly identified using Markov clustering. We see orange clump here, pink clump here, gray clump here, red clump here. As expected, interestingly enough, near the boundaries of some of the clumps, we see individuals that straddle multiple social groups, and those individuals are a little bit harder to classify, but more importantly, the very fact that we can discover the social groups and their boundaries is incredibly valuable. And for social graph data companies like Facebook or LinkedIn, being able to do this analysis is incredibly valuable. We did this using the Markov clustering algorithm, uh, a very simple algorithm that's basically built around matrix multiplication and probability theory, and is empowered by the very same concepts that power billion-dollar algorithms such as PageRank, and again, which is very easy to execute using numeric Python libraries uh, such as uh, uh, such as NumPy. So there we go. We've effectively learned how to uncover friend clusters of friends in social graphs, and I hope you enjoyed my talk, and have a great evening. Thank you, everyone.